Today we're going to the whole lecture talking about coding, and hopefully we'll get to the end of that so we can have a very relaxed final lecture next week. So before that, let me start with the announcement and an apology concerning the homework that was due for this week. So you saw that shortly after posting the homework, we realized that one of the problems was actually correctly listed with the wrong number. As it turns out, there was another one, which we just realized today, thanks to Shruti for bringing that to my attention. So the last problem in the homework set was not the one I meant to assign to you guys. And you might have seen that it was a very hard problem. And that is the reason. So it can be solved using some tools that we didn't quite cover in class. So I apologize for that mistake. And we're not going to count it towards the grade. Now, if you did solve it, then by all means, turn it in with your homework. And we'll take a look. And if you got it right, we'll keep that in mind for your final grade. But you're not expected to do it, so I apologize, especially if some of you spent some time trying to work it out. What happened is that I have a preprint of the book that had the wrong problem numbers on this particular chapter, so it's driving me crazy. So with that, we'll get into coding. And let me start by reviewing what we saw last week. This is an important topic. It's a little bit dry, so bear with me. I'll try to make it as amusing as possible, but it's very mathematically based, and I'll try to see if I can give you some intuition. But it is important. It is an important ingredient in wireless communication. So it is certainly appropriate that we spend at least one full lecture and some time we spent last week on it, so you at least end the course with a feel for what the role that coding plays, which is a very important role. So coding is essential for reliable communication, and as we saw in the information theory part, as long as the rate is below the capacity, by using sufficiently powerful code, we can make the error probability as small as we want. Just we throw at it more and more complexity, we're using more and more sophisticated codes, we can make the error rate very, very, very small. Okay. So of that improvement brought about by coding is the coding gain, which is the reduction in SNR required for a given error probability. So say I tell you, okay, I want 10 to the minus 3 bit probability error, right? So if I don't use any coding, that's going to require some SNR. Now, if I use coding, I can achieve that same error probability at a much lower SNR. And that's the coding gain. That's how much power I'm saving through the use of coding. So as I said, modern cellular systems use very powerful coding schemes. And towards the end of today's lecture, I'll try to give you a glimpse of what kind of codes are used in your cell phones. It is also used in any digital communication system. It's very used in DSL, cable modems, digital radio, satellite, everything really. So whenever you have to communicate digitally, you always put coding on it. So mostly we'll talk about codes for unfaded channels, and then at the end we'll just touch a little bit on what happens with fading. So I took you through this baby example of the parity check, where what you do is you add one bit you take a group of bits and you add one more bit, so that the total number of bits of ones in the block is either even or odd. Okay, that's a very old code. And it's limited. It allows you, for example, to detect an odd number of errors. But it's very simple. So it's a very easy way of getting some protection against errors. It doesn't allow you to correct errors, but you can detect certain errors when they occur. And that naturally extends into linear block codes. So linear block codes build on this idea of parity checking, but instead of using just one bit for parity, they use a group of bits. So the idea in a linear block code is that you take a group of, let's see, we take a block of k information bits, and we map it into a code word of n coded bits. So n is always going to be bigger than k. And so this forms an n comma k binary block code. The rate of the code is just k over n, and so the data rate is k over n times the symbol rate in symbols per second, which is 1 over the symbol time. Okay? So this will tell you how many symbols per second you're sending, and then here you're saying how many information bits you're sending per symbol. Now, if we have k bits, k information bits, we have 2 to the k possible combinations of k information bits. Right? And we're going to have code words of n coded bits. So we have 2 to the n. Yeah, okay. So we have a pool of 2 to the n possible code words, of which we're going to choose 2 to the k. Okay, so the construction of the code is a selection of 2 to the k code words out of a total possible 2 to the n, and then the mapping of these 2 to the k code words to all these 2 to the k groups of information bits. So we saw that there are 2 properties that a code must respect, block code, in order to be linear. So one of them is that the all zero code word must be one of the code words in the code book. And then the other one is that the binary sum of any 2 code words should give us another code word. And remember, the binary sum means that the sum of 2 ones is equal to 0. Okay, so 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. So here's an example of a very simple code, which has 4 code words. So k is equal to 2, right? We have 2 to the 2, which is equal to 4 code words. And the code words have 3 coded bits, so n is equal to 3. So this is a 3,2 code. And it's linear, right, because it has the all zeros. And if you add up any 2 of these guys, you're going to get one of the other ones. All right? So for this code, the pool of code words, there are 8, right, possible code words. There are 0, 0, 0, 0, 0, 1, 0, 1, 0. These are the pool of 8 code words, and we've chosen 3 of them, right? We chose this one, then we chose this one, and this one. So we chose these 4, and we built our 3,2 code. So we can send 2 bits. Using 4 code words, we can send 2 bits. We can send the messages 0, 0, 0, 1, 1, 0, and 1, 1, right? So we can send these 4 messages using these 4 code words. So we have to map each message to one of those code words, and we have a code. Very simple, but it's a code. Yes?
That was a 3,2 block code? Wouldn't that be because just on the previous slide, you said that the rate would be k over n.
Right, the rate here is 2/3. The code rate is 2/3, the code rate. K over n.
Yes, that would be 5 at 3 over 5. Because then every 3 bits have 2 bits that are
For every 3 coded bits that you send, you actually send 2 bits of information. So it's 2/3,
okay.
right? Does that make sense? All right, so in order to get protection against errors, we want, of course, the code words to be as far apart from each other as possible. So we have to define the notion of distance between code words. And for binary codes, a good notion is the notion of Hamming distance, which was something that was coined by Mr. Hamming, of course. So the Hamming distance between 2 code words is just the number of digits in which they are different, right? For example, between these 2 code words, 00101 and 10011, the difference is 3. There are 3 positions in which the code words are different, right? And so for the whole, if you look at the whole code, like this one here, right? The minimum distance is the minimum distance between any 2 code words. So for this one, it's clearly 1, right? Because there are some of these just different by 1 digit, like here, these 2 guys, for example, right? So for this code, the minimum distance is 1, which is not very good. So the larger the minimum distance, the more protection against errors. And we'll get back to that. Now, an interesting fact of the fact that an interesting advantage of codes that are linear is that they have this property, which is that the minimum distance happens to correspond with the distance between the all 0 code words and any other code word. So rather than just looking at all the possible combinations of code words and looking at the distances, you can just look at the all zeros and see which is the closest code word, in this case, this one. And the minimum distance between the all zeros and any other code word is automatically the minimum distance in the code. So that simplifies the task of finding the minimum. Next one is the weight, which is the number of ones in a code word. And from what I just said, it follows that the weight also equals the distance between the all zero code word and any other, right? Weight of particular code word equals the distance from the all zero code word. Okay, so now what remains to see is how we map code words to messages, right? Here we have 4 messages and we have these 4 code words. So how do we map, how do we say, okay, which message goes with which code word? Well, we're going to do that using a matrix, which is called a generator matrix. So it's a K by A matrix. It has K rows and N columns. And if you take a message of bits from U, right, which has K bits, and you just multiply U by G, which is the matrix for the code, you obtain C, which is a vector of coded bits, right? So just matrix multiplication by the information bits. So it is automatically the code word that we want to use for that particular group of bits. So this matrix has some properties, which is essentially that it's full rank, so it has rank K. And if you denote by little g each of the rows of capital G, you can easily see, looking at this multiplication, that the code word is just a weighted combination of the rows of G. So you take each row, weighted by the corresponding information bit, 1, 2, 3, 4, 5, up to K, and that gives you the code word. Now, a very common class of codes is the class of systematic codes. And what that means is that the generator matrix G starts with the identity matrix, okay? And then the remaining of it is arbitrary, so we can call it P for parity. So G moves like this. It's I for the identity, and then is some other matrix P, as you can see up here. What that means is that if we multiply this G, the G with this structure, by a vector of bits U, we get that the first K bits, coded bits of the code word, happen to correspond with the information bits themselves, because the identity doesn't alter anything, it just carries them through. So the code words start with the information bits plus some additional bits which are called parity bits, which are found by an inner combination of the rows of the matrix P, which is the latter part of the matrix G. Okay, so it's a special case where each code word is formed by taking the information bits first and then adding some parity bits, which are found through an inner combination of these information bits with the rows of this matrix P. And we can take any code and make it systematic by doing operations on the matrix G. We shall not get into that, so you can just forget about it. Okay, let's see an example. Let's consider a 7,4 systematic code. Okay, so this is the corresponding generator matrix G. You see the first 4 by 4 block is the identity, and then the remaining 3 by 4 is the part P of the matrix, the parity part. Now, if we have a block of 4 information bits, U1, U2, U3, U4, the code word is obtained by multiplying this vector by G, and so it's going to be U1, U2, U3, U4, the same information bits, plus 3 parity bits. Now, it's very easy to see how to compute the parity bits within the matrix, right? Because all you have to do is an inner combination of the rows. So the first parity bit, P1 over here, is found by looking at this column. Okay, the first column of the parity part of the matrix. And whenever you have a 0, it means the corresponding information bit is not involved. When you have a 1, it means that the corresponding information bit is involved. Because what happens is that linear combination multiplies by 0 by 1. You multiply by 0, you disappear. Multiply by 1, you remain. So let's look at this guy. Yeah? 1, 1, and 0, 0. That means that we have to keep U1 and U2, and we throw away U3 and U4. Okay, so the first parity bit is just U1 plus U2. Now, how about the second parity bit? It's going to be U1 plus U4. Okay, these two guys, 2 and 3, just have zeros, so they don't appear. Okay, so U1 plus U4. And the last one is going to be U2 and U3. Okay, and 1 and 0 don't appear. So U2 and U3. And that's it, right? You get the hang of it, right? Just look vertically position by position, and just look at the guys that have a 1. Those appear here added up. The ones that have a 0 don't appear. And that's it, right? So this relationship tells you how to compute the 3 parity bits, and you add them to the use, and you have your code word. Now, this is very easy to implement. That's why systematic codes are so popular. So let's go to figure 8.2. It's kind of interesting to see. Okay, here it is. So you take, we have our 4 information bits, 1, 2, 3, 4. Just ignore these I's, I don't know what this means. And from these, so these go automatically outside. You have a switch here. First, you let these 4 guys go out. And then you toggle the switch to the up position, and you get the parity bits to add onto those, to funnel those. Okay, so that's how you're going to build this sequence of, you have the use first, and then the P's. Okay, so one way to do it is you just have a switch, and that's actually how they do it. Have a switch first. This is memory. This is stored in memory. Have a switch. You read out these 4 guys, and then you read out these 3 guys by switching up here. So how do you compute these 3 guys? Well, you just add up the corresponding ones, right? We just said that P1 was U1 plus U2 over here. So what you do is you take U1 and U2 and you add them feed them into an adder, and the output is a P1, right? Similarly, P2 is obtained by adding U1 and U4, and P3 by adding U2 and U3. And that's it, right? So it's a very easy way to construct an encoder. So this encoder, you just read in the use coming from your source, whatever it is. It could be your MP3 player, whatever you're using. And this guy is going to produce the P's just by combining these U's, and then you just read out the U's and the P's, and you have your code. It's a very easy way to build a code, an encoder. So that's pretty much how you encode block codes. It's just a bunch of shift registers and others. Now, how do we decode it? Decoding is always much harder than encoding. So when we receive a code word corrupted by noise, how do we decide which message was actually sent? Well, here are some tools. Associated with every generator matrix G, there is something called the parity check matrix H. So let's focus on systematic codes, right? So G is going to be the identity plus a parity matrix, as we just saw. So the corresponding parity check matrix H is built simply by transposing P and then adding the identity. That's it, right? So you just take this P, you just transpose it, then you add the identity, and you're all set. Now, you can easily verify that these matrices satisfy this property. G times H transpose is equal to 0 by construction. So if we multiply a code word C by H transpose, when you get that, remember that C was equal to U times G, right? We just saw that 2 slides ago, 3 slides. C is equal to U times G. So we replace C by U times G, and we get U, G, H dagger, and I just told you that G times H dagger is equal to 0, right? So something times 0 is equal to 0. So something is equal to 0. So point is, multiplication of any bounded code word C by H transpose results in a vector that has all zeros, all right? So say we received a vector R, which is a bounded code word C, plus some errors E, right? Some flipped bits. So this is the error pattern that has a 0 where there was no error, a 1 where there is an error. Now, we can define the syndrome of R, of this received vector R, as the product of R times H transpose. Now, remember what I just told you, right? So let's use that. The syndrome will be the all 0 vector if the code word is not corrupted, right? Because if R that we receive is equal to a code word C, then I just told you that C times H transpose is equal to 0, right? So if R is equal to a code word C, then this is equal to 0. So the syndrome is 0 if the code word we receive is a bounded code word, so it has not been corrupted. Now, if the error is detectable, then the syndrome is going to be non-zero. Now, what does detectable mean? Well, it could happen that the code word is sent, some errors take place, and they flip the code word into a different code word, right? For So imagine that I send this code word, 001, and the last bit is flipped in error, so I receive, I send 000. The last bit is flipped in error, I get 001. Well, this is still a valid code word, right? So as far as I'm concerned, this could have been sent. So I cannot detect this message using the syndrome. And in fact, I cannot detect this message in any way. So when you have an error of this type, it cannot be detected. But if I send 000 and the 3 bits flip, so I get 111, this is not a valid code word. So I look at the syndrome, it's going to be non-zero. Okay, so I can know that an error took place in this case. So some errors are going to be detected, some errors are not going to be detected. All right. Another point about the syndrome is that given a certain syndrome S, there is not a unique error pattern that causes that syndrome. So the syndrome is only so useful because what happens is it allows you to detect certain errors, but you can never know which error took place. So there's more than one error that's going to map onto the same syndrome. So it's a very good way to detect errors. It's not useful to correct errors, right? So it allows you to detect some errors, but you can never pinpoint where the error took place, all right? So that's the appeal of the syndrome, which is limited. Now, final comment here, a very useful class of linear block codes are the cyclic codes. And all I'm going to tell you guys about this, just so you know that they exist. And what makes these codes cyclic is the fact that each code word is a cyclic shift of another code word. For example, this is a cyclic, this is a 3,2 cyclic code, right? So except for the 000, all the other code words are just shifted versions of each other, right? You shift this guy, you get this guy, you shift this guy, you get this guy, you shift this guy, you get this guy again, right? When you shift to the right, whatever comes out comes back in from the left. Okay, so it's cyclic shift. So these guys, except for the all zeros, all the other ones are cyclic shifts. Now the all zeros is also a cyclic shift, right, of itself. You shift around 000, you always get 000, right? So this is always self-shifting. Now the other ones are shifting, mutually shifting. So why is this good? Well, what happens is that when a code is cyclic, you don't have to use these matrices that I just told you about. You can actually use polynomials. So the whole thing becomes polynomial based. So the coding and the decoding is all based on polynomials. So there's a huge theory of polynomials that can be used for these tasks. Yes.
For a cyclic code like this, it would be better if it was 00 and 110. Okay,
Yeah, I'm not sure there was an attempt here to make this a good code. It was more for the example of.
Okay, because it'd be better.
Because what happens is that it's not a very good code because the distances between the code words is just 1, right? So the point is to illustrate the cyclic property, right? I don't think there was any. So I took this from the textbook, but I don't think there was any attempt to make this a good cyclic code, right? Yeah, it's not. It's a useless code. When the distance is 1, it's a useless code. Just like that one too. Yeah. And we'll see in a second why that's the case. But you're right. Okay, so let's focus on decoding. That's all I want to say about coding of block codes. Now, decoding is harder than coding, as usually happens. So let's start with hard decoding. Hard decoding means that the modulator and the decoder don't work together. Okay, so this is a very important distinction. Let's make sure that we understand. Okay, so we get our signal coming from the channel, from the antenna, essentially. So for now, we're going to focus on hard decoding. What happens is that the modulator demodulates the signal, ignoring the fact that the signal is coded. So remember what we saw for the constellation? You take your constellation, right? You receive a point in the constellation, you map it to the closest point in your space, right? You make a decision based on proximity. And you output the corresponding, if it's QPSK, you say, okay, this is the closest point, so I'm going to decide this is the point. This point was the point 1, 0, so I output 1, 0, whatever it is, right? So the modulator works as if the signal was not coded. It makes a decision on the bits based on the proximity points in the constellation, outputs that, and sends it to the decoder. Okay, so you take a group of these symbols, that makes a block. The decoder receives an input that is a string of zeros and ones produced by the demodulator. And then on this string of zeros and ones, some of which may be in error, the decoder tries its best to guess which of the messages was actually sent. Okay, so that's what I mean with hard decoding. Now the decoder is going to compare, so let's call R this vector of ones and zeros that is outputted by the demodulator. Okay? Now the decoder has to compare this R to all the possible bounded code words, there are 2 to the k bounded code words, and decide in favor of the one that's closest in having distance. Okay, that is actually the optimum strategy. So it's quite intuitive, right? So we have to select the code word J, which has the minimum distance from the received vector R in the Hamming distance sense. So the minimum number of positions in which the zeros and ones are different. If there happen to be multiple code words at the same distance, minimum distance, then we just choose one at random because we really don't know in that case. So as it so happens, this strategy is optimal when we're doing hard decision. And it can be shown that it's equivalent to a maximum likelihood criterion. Remember that we saw this notion in the demodulation chapter. So what I just told you, picking the one closest in Hamming distance can be shown to be equivalent to picking the one code word C sub j that maximizes this probability, right? The probability that we receive a vector R given that particular C sub j is bigger than for any other C. So that's the optimum C. The one that we want to choose is the one which maximizes the probability of having produced what we actually received. So there is a very nice graphical interpretation of this in figure 8.3 in your book. Okay, here it is. So we can interpret each code word as being inside a sphere of a certain size, and let's call it T. So this would be one code word, C1, C2, C3, C4. Okay, and these little dots, these smaller dots that are not black, that are gray, indicate receive vectors that are not code words. Okay, so let's say that we have a code with n positions. N is the number of coded bits per code word. So for example, in this case, there are 4 code words, right? So n will be equal to 2, right? I'm sorry, it's going to be k is equal to 2. N is going to be whatever, we don't know. It can be whatever it is, right? So these code words are going to be vectors of length n. Okay, so there are 4 of them that are bounded, and all the other ones that are like little flips, like we saw here before, right? We flip one bit or another bit, result in other vectors that are in this space that don't correspond with any of the code words. Okay, now we can draw a circle around each code word, right, of a certain size t, so that the circles touch exactly. And so what happens is that for example, if we receive this point, right, which code word are we going to think that was sent? Right? The center of the corresponding circle, right? C2. Because it's the one that's closest in Hamming distance. So the distance in this space, is Hamming distance. Right? So these guys are probably 1 bit away from the code word. So 1 bit was flipped. These guys are probably 2 bits away, and this guy is 3 bits away. Okay? So there are 2 notions that are important here, 2 distances. One is the size of the spheres, which in this case is 1.5, right? So what I just told you is this is 1 bit away, right? And this is 1.5, this is 2 bits. And then the distance between code words is 3 bits in this case. So to go from one to the other, you have to flip 3 bits. Yes? Because of the fractional. Yeah. Yeah, what happens is, in fact, let me defer that for like 2 minutes. I'll come back to it. It's a good point, right? So the intuition here is that, let me go back to the slide first. So each code word is inside a sphere of size d min divided by 2, rounded down, which now goes to your point, right? So if this is not an integer, if it's a fractional number, like something 0.5, we have to round it down to the lowest integer. So if t is 1.5, it's rounded down to 1. So we're losing that half. We're losing that half actually. It's lost, right? So the distance can be okay. So what happens is d min is the distance between two code words, right? So in the picture, I know for a fact this is 3 here in this case, right? It's 3. It's 3 between code words, right? So it means that you have to flip 3 bits to go from one bounded code word to another bounded code word, all right? So d min is 3. Now t is the size of the spheres is 1.5 in this case, right? Now what happens is the actual sphere is 1.5. Now t really, see the picture is kind of unclear because t is actually rounded to the closest integer. So in this case, the 1.5 becomes 1. So even though here, so you see the size of the sphere is 1.5, but what matters is that the point in the sphere that's the farthest away is 1 away, right? Because the next one is already in the next sphere. So in this case, the size of the sphere is 1.5, but the t as defined here is 1.5 rounded down to 1. So now let's say that we want to use this code to just detect errors. We don't care we just want to know if there was an error or not. Okay? So how many errors can we detect based on this in terms of distances? You think we can detect t or d min distances or which other quantity? Anybody wants to take a guess? We can detect 2 errors here, right? So we can detect, in fact, you can generalize, you can detect t min minus 1, right? Because as long as we don't go exactly all the way to the mean, we're never going to reach another code word, right? So, in other words, to have an error that we cannot detect, we need to go from one code word to another code word, right? And that's the distance of the mean, right? So we can detect up to the mean minus 1 errors, because then that means that we're not going to quite get to another code word. We're going to end up in somewhere in nobody's in no code word space. Right. So it's gonna put you outside of your sphere, but it's not gonna put you in another code word, right?
Well, once it's going to put you outside of the sphere.
Yeah. So I'm just telling you, that you can detect an error, right? You can detect that you received something that at least one bit was flipped, right? Because you detect something that's not in the center of a sphere. Now, if you get exactly d mean errors, you can actually get pushed into another center of the sphere. So the decoder is not going to notice anything. It's going to think that the channel is clean when it's not, right? So you can detect d min minus 1. Now, how many can you correct, to your point, right? How many can you correct, right? Just t, right? Because, so as long as you stay within your sphere, because the decoder is going to always say that what you send is what's in the center of the sphere. So as long as the message falls in the right sphere, the detection is going to be correct, right? So as long as the number of errors doesn't exceed t, the decoder is going to actually give you the correct answer. It's going to guess the correct code word. So in other words, the capability to correct errors is weaker than the capability to detect errors, right? So you can detect, I think it was somewhere over here. You can detect up to d min minus 1 errors, okay? But you can, in fact, if there are d min errors, then we will obtain another bounded code word, and the detection will fail, right? But we can only correct up to t errors. Okay. In fact, how many errors? This is a more precise quantification, right? We can detect 2 to the n minus 2 to the k error patterns, because there are 2 to the k minus 1. Okay, there are 2 to the n there's a pool of 2 to the n potential code words, of which we're using only 2 to the k, right? So, except in the case that the code word becomes another code word, in all the other cases, we can always pick up the error. So, except for 2 to the k possibilities, for all the other ones, we can detect the error. So, we can detect 2 to the n minus 2 to the k error patterns, but we can only correct a few. We can correct only errors of up to t errors per code word. So t bits flipped per code word.
This is equivalent of saying d min minus 1.
Let me see, you were saying as opposed to this definition of t, d min minus 1 divided by 2. Yeah, what happens if d min is even, right? If d min is 4, then 4 minus 1 is 3 divided by 2, 1.5. So, but you have to round it down always. So this has to be an integer. So you say d minus 1 divided by 2, round it down. Is that what you're saying?
Yeah, you cannot correct d min divided by 2. You cannot correct, if you have d min equals 4 divided by 2, you cannot correct 2 errors.
Well,
You never know if it will be
yeah, what happens, this is a,
the two.
you have a good point. So what happens is that in that case, you're going to be exactly on the boundary of a sphere, and you may be in the boundary of 2 spheres, so you may have 2 possible code words to choose from. You're probably right. So I believe I took what was in the book. I don't know if anybody can check, but I think you're right. I think that in the case that this is even, what happens is that you may have 2 code words or 3 to choose from, of which you don't know which is the right one. So that is possible. So if you do d min minus 1 divided by 2, then you're guaranteed to have only one option. Now, of course, this is correct if d min ends up being odd, right? Okay. Okay, so let me check that. No, because what happens is that I'm not 100% sure that, you see, you want to be on the boundary, but it may be that you're in the boundary of only one sphere. So it's not the same to be on this point here and to be on this point here, you see? Because here, even though you're in the boundary, you know that this is the right code word. Now, if you are here, then you have 2 possible solutions. So it may be the case that never happens. So, but I'm not sure. So,
I proved it in my information series, so I'm not.
is that right?
very-
So I'll check on that. It's a very good point. So thanks for bringing that up. So the contention is whether there is d min or it has to be d min minus 1 here.
That's for the numbers, the error you can correct.
Okay, so I'll check on that definitely. Okay, so here's another example, I think also taken from the book. Well, this is kind of a trivial thing, right? Let's take this 5,2 code. So there are these 4 code words of length 5, right? So which are the undetectable errors when we send all zeros? And the answer is the other 3 code words, right? This is trivial, right? So as long as we don't receive any of these guys, we can detect an error. If we receive one of these 3 guys, then we're gonna think incorrectly that there was no error, right? But there's no way around that. I mean, there's no way that you can get around the fact that you send a code word and you receive another code word. There is no way that you can detect that error if it's just beyond the code's, potential. But anyway, just making that point here again with the example. Okay. So I think we already covered this. We can detect up to t errors. There are error patterns, those that bring you into another sphere, that can be detected but will be wrongfully corrected. All right. So this raises the issue now of what's the probability of error, right? So let's assume that the detector tries to always decode and correct the errors. Sometimes it's going to incorrectly correct the errors. So that's what we're going to be talking about now. So let's say we had decision, right? We just said that we can detect up to t errors, and the definition of t is what we have to verify. So we receive a code word, a vector r, and we can correct up to t errors in this vector r. So Let's assume that the errors happen independently. Okay, so we have this this vector R has n-coded bits. So let's say these n-coded bits are flipped in error or with some probability independently, one from the other. What's the probability that a particular bit is flipped in error by the demodulator, right? And it's passed on in error to the... Well, that's what we studied before, right? We spent like 3 weeks talking about this. So if this is BPSK, what's the probability of error, right? It's a Q function, remember? Q function of the square root of gamma sub B. Remember all those formulas? Right? So whichever consolation you're using, you have the formulas you've used them before, compute the probability of a bit being in error at the demodulator, right? So that's PB here. Now we have a group of n bits, and we assume that they flip independently with probability PB. So the way to compute if there's going to be more than t errors in the vector R is by this formula, right? You have an n choose j, and j adds from t plus 1 to n. So n choose j, and then you have the probability that a bit flips from 1 to 0, from 0 to 1. Okay, so just a combinatorial summation. And the reason it's a bound is because of this assumption of independence, which may not be true. But it's a good quantification of the probability that we're going to have more than t bits in our received vector. And if that happens, then the error is not going to be correct at all. Now, this formula is kind of messy because of the combinatorial nature, right? So it has this n choose j, so it has all these factorials. So there's a formula that's more convenient to work with. It's easier to compute, although it's a little, it's less tight. But it's up here, okay, for your convenience. And this one depends on the mean of the code. So it's just easier to compute, and it's a Moser bound. About PEC, probability of error for the code. It's for the whole code word, right? This tells us the probability that the code word is mistaken by another code word. Now, code word has n bits. Actually, sorry, has k bits, k information bits. I encode it in the code word. So what's the probability that the particular bit is in error, right? So now that depends on how we map bits onto code words. And remember that the notions of gray mapping that we saw in digital modulation, right? So what do we want to... We want to have... Okay, so say we have 2 code words that are at minimum distance, okay? Do we want these code words to have many bits that are different or very few bits that are different? Which case do you guys think we want? Do you prefer 2 code words that are very close to each other to differ in few bits or in many bits? Few bits, right? Because if we make a mistake between these code words, and this is the problem mistake, right? Because these are a minimum distance, we want to make sure that the fewest number of bits are flipped, right? Remember what we saw in gray mapping, right? 2 points that are neighbors in the constellation, we want to make sure that they only differ by 1 bit, right? So here's the same thing. You want to make sure that 2 code words that are at minimum distance differ by as few bits as possible in terms of the information bits, okay? So the message bits, all right? So if we do that carefully, then it works out that the probability of a bit in error is just approximately the probability of the code word in error divided by k, where k is the number of bits in the message, okay? So it's the same thing we're doing for gray mapping. In gray mapping, we're saying, okay, PS is equal to, PB is equal to PS divided by k. So here is the same thing, except with the code, right? So it's the same idea. So as long as you're carefully mapping bits onto code words, you can approximate the probability of bit error as the probability of code word error divided by k. So that's it for hard decoding. Now we'll get into soft decoding, and that'll be the end of the block codes we're doing. All right, so we'll see this part and then we'll take the break, right? It's just 3 slides, so bear with me, guys. Okay, so what's the difference between soft decoding and hard decoding? Let me see if I can exemplify. This is very important. So I just told you for hard decoding, the demodulator makes a decision on the constellation based on minimum distances on the constellation space, and then output zeros and ones onto the demodulator. All right? That's for hard decoding. Now for soft decoding, we're going to do something better. Now, what's the problem with this? Let me give you let's see if I can manufacture a baby example. Okay, let's say I have the simplest possible code. It's called a repetition code, actually. So it has 2 code words, 0, 0, and 1, 1. So if I want to send a 0, I send 0, 0. If I want to send a 1, I send 1, 1. It's repetition, right? So you increase your chances that at least one of the 2 bits is not mistaken, right? So you just take your bit and you repeat it. Okay. Now, as it turns out, I'm going to send 0, 0, okay? I'm going to send 0, 0, and what I've received is 0, 1. So the second bit was flipped in error. Now, I'm in trouble, right? Because what am I going to say? I'm the decoder now. I received 0, 1, and I know the code is 0, 0, 1, 1. What do I say? What was sent? We have no idea, right? It's an error. We just say there's an error, right? With hard decoding, that's all we can say. Now with soft decoding, we can do better. So let me see if I can get you the intuition to you, right? So I'm going to tell you more than this, right? So I'm going to tell you exactly what the constellation saw. Okay, so say I was using BPSK, okay? Using BPSK, so this is my IQ plane. So BPSK has 2 points, right? So the point with amplitude A and minus A. And I'm using minus A to send a 0 and plus A to send a 1. That's my BPSK. Now I send 0, 0, and what I received is the following. I received the first symbol I received, of the output in my antenna was here. So I said, okay, that's a 0, right? The second I received was here. So I said, okay, that's a 1. And so I said, okay, I have 0, 1. Right? So if I just tell you I got 0, 1, you have no idea what was sent. Now, if I tell you I received these 2 points, what do you think is more probable? Send 0, 0 or 1, 1? 0, 0, right? Because this guy is clearly a 0, and this guy is 50, 50, right? It just happens to be exactly a little bit on the right, but it could have been a 0, 2, right? So the soft decoder is going to use this information. So what's going to happen is that the modulator is not going to send 0, 1 to the decoder. It's going to send this number and this number. The decoder is going to use the proximity to the points to make a more accurate guess what was sent. So that's the idea. So, yes?
Say that this proves my example that I was saying before. If you take d min is equal to 2, 2 divided by 2 equals to 1, and you cannot correct 1.
You're going to correct 1 error, yes, yes. Yes. Yes, you're right. So that may be yet another type of the book. Yes. Okay, thank you. That's a good point. So I made the homework for you. All right. So how can we use this soft information? So we're just going to focus on BPSK, okay, just for simplicity. Of course, you can do this with QPSK too and with other constellations, but that's going to suffice for us. So I'm going to just recap some quantities, right? In encoded BPSK, we had gamma S and gamma B that were equal, remember? Because it's just 1 bit. So these guys were equal. And one is the energy per symbol over N0, the other one is the energy per bit over N0. Now, in encoded BPSK, we're going to replace the symbol S with C, okay? So instead of ES, we're going to talk about EC, just because it's coded. So it's a distinction. The book makes a distinction of coded symbols versus uncoded symbols. So the relationship between EC and EB now is not anymore equal. They're not equal because there is a K to N ratio. Okay, so for every K bits, information bits, we send N coded symbols. So there's a K to N ratio between the energy per bit and the energy per coded symbol. So let's say the amplitude that we're sending here, this A minus A, are these, right? So A is square root of EC, and minus A is minus square root of EC, right? So this is A plus noise, right? So if the code word digit is 1, we receive amplitude A plus noise. If a 0 was sent, we receive minus A plus noise. Okay, in this case, exactly corresponds with what I was just showing you on the board. So we get a vector R of little r's, each of which is either plus A or minus A plus the corresponding noise. Now the decoder receives this soft information and has to now make a decision on which was the code word that was sent, right? So how it does it is it computes a correlation metric. I'm going to C, and careful here, this is not capacity, it's the same C, but it means correlation here. So the correlation between the receive vector R and a particular code word I is this summation for all the bits in the code word, all the symbols, of this product of 2C of J. So this is the ith code word, the jth position in that code word, 2Ci of J minus 1 times R sub J. What does this mean? Okay, this is simpler than it seems, right? Of the operation 2C of I of J minus 1 simply converts ones and zeros into into ones and minus ones. Okay, so we're just going to take our ones and zeros and map them to ones and minus ones, like here, right? So we're going to map the ones to this point with amplitude 1 and the zeros to minus 1. Okay, so we're just converting ones and zeros into ones and minus ones. And the amplitude really is irrelevant here. And then we multiply these by the corresponding received values. We just add up over all the positions. And we pick the one that's the largest, right? So how do you compute this metric for this baby case? Well, let's see, right? This code word becomes minus 1, and this code word becomes 1, 1. Okay, so we have minus 1, and 1, 1. And then what did we get? Well, we got, let's say this guy, so let's make the amplitude 1 just for simplicity, right? This guy, I'm going to say, is minus 0.9, right? That's more or less what I was intending. This guy, I want to say, is 0.1, right? So I compute my correlation by saying, okay, for the first code word, the correlation is minus 1 times minus 0.9, right? So this is 0.9 plus minus 1 times 0.1 is minus 0.1, right? So if I didn't make a mistake, I get the 0.8 for the correlation between the received vector and the first code word. Now for the second code word is 1, 1, right? So I get minus 0.9 times 1 plus 0.1 equal to minus 0.8, right? Appears to be that way. And so which one do we get? We pick the strongest one, right? Which is this one. And so we choose the 0, 0, which was the correct code word, right? So we made the correct decision. So as you can see, there is a pretty big difference between the two code words, between the two correlation values, even though for the hard decoding, we didn't know because 1, 0, 1 could have gone either way. When you compute the correlation, as you just did, you get a pretty big difference, right? So it's clear that the first code word has a much higher probability than the second one. So that's about it in terms of the correlation. Yeah.
So CI is the minus 1, minus 1.
No, CI is the 0, 1s. So 2 CI minus 1 is what converts 0, 1. So the C itself is zeros and ones, right? So when you do twice the C minus 1, what happens is the ones remain ones and the zeros become minus ones, right? So you get the right polarity for BPSK. If this was QPSK, you had to do a different operation here. Be careful. And this is only valid for BPSK. So for QPSK, we have to convert these into ones, J's, minus 1s, so it becomes more messy.
For the first one, we're saying what we got was just 2 times.
Right. So the 2 times C minus 1, I did it here very quickly, mentally. This became minus 1, this became 1, 1, right? Now, the correlation I did by hand, multiplying entry with the corresponding entry of the vector, which was at these two values. You just add them up. And then you get two numbers, right? The correlation between the received vector and the first code word was 0.8. Between the received vector and the second code word was minus 0.8. This is a coincidence, that they flip signs. And this could be at different numbers. It just happens that in this case, it just shows numbers that happen to give us the same number with different sign, but it's just a coincidence. So now we want to pick the biggest of the two. right? And accounting for the signs. So we want to pick the 0.8. It's bigger than minus 0.8, right? So essentially, the computation of this metric accounts for the distances between the points, not just for if it's a 0, 1, but actually what and I, how close it was to the 0 to the 1. So that's how, yes.
You had a large error in one bit. That
It biases the metric, right? Yeah.
not just a few bits, so it's okay.
Yeah.
You had a very large error on one single bit to record the whole.
Yes, that's exactly right. So a particular, a huge error, like a huge noise sample in one particular point is going to bias the whole correlation, right? So you can have, theoretically, right, you can have situations where one single error pushes the metric higher than another one that had 3 or 4 little errors, right? Things like that. Right. 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 No, you're exactly right. And what happens is that that's why this is very important in the distribution of the noise, right? So this correlation metric is optimized for Gaussian noise, where the values have a very nice soft distribution, right? Now, for example, if you had like impulse noise, which would have a behavior like the one you described, right? Like you may have little errors here and there, and then a huge error, like a spike type of thing, right? Then you could find that this performs worse than the hard decoder, for example, right? I think I'm sure you can build an example where that happens. So definitely the soft decoders have to be optimized for the particular noise. And in that case, you will have to use a different correlation function that doesn't give so much weight to the distance. So your point is very well taken. So this derivation in the textbook is only optimized for Gaussian noise. So you could definitely come up with noise distributions, especially if they're very bursty, where this is going to end up doing worse than the hard decoder. It's a very good point. Other comments?
The case where yours is the average efficient goes with n equals 3, right? So if n equals 3, then you could have minus 0.9 two times, and then one speed at 3.
Yeah, which would overweight the other two. Yeah. Well, possibly, right? Possibly, because in this case, you may actually have the three of them in error, something like that, right? So it has to be for the hard decoder to do. You have to have a few very large errors, but then the other ones have to be not in error, right? Because the hard decoder has to have few errors to do well, right? So you can construct careful examples where that happens. Usually the top decoder works much better than the hard decoder. Points, definitely. So there's an issue here with the noise distribution that certainly this may not work well for certain types of noise. Definitely, very true. Okay, so let's very quickly look at the error probabilities for soft decoding. It's a little more involved, so we just sort of glanced over it. Because in Gaussian noise everything is symmetric, we can just focus on the all zero code word, so C sub 0. And so what's the probability that we send C sub 0 and we mistakenly choose another code word at the detector? Well, we have to compute the probability that the correlation between the received vector R, even though we send C sub 0, the correlation R, if it's smaller than the correlation with another code word, I, we're going to choose for I, right? So what's the probability that this happens? And this connects with the stuff we were just discussing, right? What's the probability that we send C sub 0 and we receive R, but then R happens to be closer in this correlation measure to another code word, C sub I, right? Well, surprise, surprise, it's a Q function. And we shall not get into the derivation, but you know, you're just computing a bunch of stuff with Gaussian noise, and Gaussian noise always ends up with the Q function, right? So it's a Q function, and the argument is the code rate, K over N. There's a factor of 2. There is the weight of the code word, and there is the gamma B. So the weight, remember, is the number of ones in the code word. All right, so I'm Unfortunately, we cannot derive this formula because it's quite involved. So now remember, this is the probability that a particular code word I has a better chance than the one that was sent, which is 0, right? Now to get the probability of error for the whole code, we need to get the probability that the all-zero code word becomes any of the other ones, not a particular one CI, but any of the other ones, right? So we can use the union bound. Remember the union bound we discussed in a few weeks ago? So when you have a union of events, you can bound it by just adding up the probabilities, right? So it's just an upper bound, but it's an easy one to compute. You just add from 1 to 2 to the k minus 1, which are all the other possible code words, you add the corresponding Q function. And there's a simpler version of this, which uses the fact that the weights are always larger than d min. So you can actually simplify this and get rid of this huge summation. Now this could be a pretty large summation, right? Like if k is equal to, I don't know, 5, right? This is 2 to the 5 minus 1. So this can be a pretty large number of terms here. So this bound is less tight, but it's much easier to compute. Now, we can actually express this in an even simpler way using some approximations, right? So we can use several ones, in fact. Okay, so I'm going to use, so what I'm trying to do is I'm trying to go from here down to here. So I'm going to use 2 to the k minus 1 is less or equal to 2 to the k, right? Since k is positive. I'm going to use q is less or equal than this exponential. Right? We saw this many weeks ago. And I'm going to use the fact that 2 to the k is equal to e to the k. No, that's wrong. Log e of 2. All right? So using these three relationships, we can take this q function, this bound, and convert it into this other one. Now, this is for coded BPSK with sub-decision, right? Now, we had found for encoded BPSK 2 or 3 weeks ago, we had this formula, right? This Q function, remember? This was the first one we found for the modulations, which was upper bounded by this exponential. So comparing these two formulas, we can actually evaluate the coding here, right? So you can say, okay, I equal these two guys with the same probability of error, and I see how much reduction in gamma B I can get going from one to the other. Okay, so I'm not going to do it, but it's an easy way to compute at high SNR the coding gain. And typically in Gaussian noise, soft decoding yields about 2 or 3 dB better than hard decoding. And relative to what we were saying before, this is for Gaussian noise. So it's not written here, but this is for Gaussian noise using this particular soft decoding strategy. Okay, so just this and we take a break, okay? So just very briefly, most common binary codes. The first one are Hamming codes, which again by Mr. Hamming. And they have m parity bits. So n is equal to 2 to the m minus 1, and k is equal to 2 to the m minus 1. So m is always equal to m minus k in number of parity bits. Minimum distance is always 3, and so we can only detect 1 error per block. Okay, so it's not very strong code, but it's very easy. And it's very old. This is really old code. Now, this is like from the 50s. Now, the Gongai code is a 23,12 code with the minimum distance of 7. Okay, so this guy can correct up to 7 errors. It's pretty common code. And there's an extended version. The extended Gongai code is 2412, which doesn't work any better, but it's easier to build because 24 happens to be 12 times 2. So it's much easier to build. And it takes a little more redundancy for the same error correction. So you actually lose a little bit. You know, you waste one more coded bit per block just to make it easier to build. And finally, the BCH code, these are the best linear codes, linear block codes that exist. And usually they have n is equal to 2 to the n minus 1 for m being an integer, usually 3 or 4. Okay, so that's what I'm going to say about block codes. We'll take the break, and then we'll finish up coding with a couple other things. Okay, final sprint. All right, so we saw block codes so far. Now we'll talk a little bit about convolutional codes with much less detail, but we'll just cover some basic notions. So convolutional codes are fairly different from block codes. They're generated by passing the information bits through a linear finite state shift register with gate stages. And that may sound pretty scary, but it's not. So let's use figure 8.5 for reference. So this is what an encoder looks like for a convolutional code. There are capital K stages, 1, 2, 3 up to capital K. Each one contains little k information bits. So this is the same thing that we had before, same quantity. And we produce code words of length n. Okay, so little k and n are the same quantities we've seen before. Now we have this new notion of capital K stages. So how does this encoder work? Well, if there was only one stage, right, you similar to a block code. Remember we saw a picture before, you have a bunch of bits, then you take combinations of some of them, and using others, you produce parity bits, right? And so that's very similar. Except that now we have k stages. So what happens is that this whole thing is shifting to the right on every tick of the clock. So on every tick of the clock, a group of k bits comes in, right? Replaces these bits here. Now the bits that were here are moved to this stage. And this stage is moved to the next stage, and so on and so forth. So when the clock ticks, everybody moves, these groups move to the right. The last group, the k stage, it just dropped out of memory. It's gone, right? It's already done its service. So each group of bits comes in, and it transverses the k stages on every tick of the clock, goes to the next stage, and then it's discarded. So at each point, we take linear combinations of the bits on the k stages to produce the corresponding code word. So in some sense, the encoder has memory, right? Because the code word not only depends on the k bit that just came in, it depends also on the other stages that are still in memory. Okay, so there is this notion of memory in the encoder. So the number of stages, capital K, is called the constraint length of the code. Okay, that's the term that it's used. So as I said, the code word depends on little k times capital K bits. And so the code has memory. And so we'll make a distinction. We call the k bits that enter the first stage are differentiated from the other bits that are inside. And the other bits are the ones that define what's called the state of the encoder. Okay, so the capital K minus 1 stages that were already in there define the state, and then there's a group of k bits coming in onto that state. So we have 2 to the k minus 1, capital K, this is, possible states. Now, there are several ways to characterize convolutional codes. There are trees, there are state diagrams, and there are trellis diagrams. So a trellis is the one we're going to be using, just a folded tree. So imagine a tree that starts with the trunk, and then it branches, and then every branch branches. Then at some point what happens is that things start repeating. And once they start repeating, we can just fold the branches onto other branches that are similar, and we get a trellis. So, hold on for a second and we'll see a picture that will make the point better than I'm trying to make it. But we're going to be using only trellises to represent convolutional codes. So these are these folded trees. So in fact, trellis diagrams. So let's see a trellis. Figure 8.6 is a trellis. Oh, wait. Before we see the trellis, let's see the code for the trellis. So in figure 8.6, we have a code. Okay. So this is a convolutional code. It has capital K equal to 3 stages. So the constraint length is 3. And little k is 1. So each stage only contains 1 bit. And n is equal to 3. Okay, so the code words have 3 bits. So every time the clock ticks, a bit comes into this stage 1, and then the guy on stage 1 moves to stage 2, the guy on stage 2 moves to stage 3, and the guy on stage 3 goes to the trash. And then by combining the different bits, so okay, let's see. The code word, the first bit of the code word is just equal to the bit on stage 1, right? the second bit on the code word C2 is equal to the sum of the 3 stages, the 3 bits in the stages. And C3 is equal to the sum of the first and the third. So that's a particular code that we're going to use as an example. So to represent this code, we can use a corresponding trellis. So the trellis is shown in figure 8.7. So this code has n equal to 3, and capital K is equal to 3 also. And so we have 2 states, right? Remember the number of states is 2 to the capital K minus 1. So it's 2 to the 2, which is 4. So what's the trellis? The famous trellis. Here is the trellis for this code. So let's spend some time going over the trellis. It's much simpler than it may seem at first. So first of all, which are the states? There are 4 states, right? 0, 0, 0, 1, 1, 0, and 1, 1. So these are the possible values that can have stages 2 and 3, right? The ones in memory. Remember that each stage has only 1 bit here. So this is the first stage, the second stage. Second and third, second and third, second and third, second and third. So we have 4 states, and then we have transitions between the 4 states. So let's assume we are here, right? We're at this point. So we are in state 0, 0. That means that we have a 0 loaded here. Okay, we have a 0 here and a 0 here. Okay, that's the state. And then something else is going to come in on the S1, right? So what can come into S1? A 0 or a 1, right? That's it. Everything is bits here. Oops, sorry guys. Wrong. Okay, so we are in the state 0, 0, and a 0 comes in, right? What's the new state going to be once the clock ticks and everything shifts to the right? Right? Anybody? 0, 0, right? It's going to have one of the zeros goes out the trash, the other 0 shifts, and then the new 0 comes in, right? It's still got 0, 0, right? So if a 0 comes in, we're going to go from 0, 0 to 0, 0, right? So in the next, so okay, this is one time. The clock ticks and we move to the next time. Clock ticks, we move to the next time, okay? So horizontal axis is time, symbol times, and the vertical axis are states. So from 0, 0, if a 0 comes in, we go to 0, 0 in the next time instant, okay? Now, what code word is produced in that case, right? So we had 0, 0, I'm sorry, let me shift that. 0, 0, and another 0 came in, right? So we have 0, 0, and 0. So which code word the encoder is going to output? All zeros, right? Because you add up zeros, you get zeros, right? So that's what the trellis shows. So we go to 0, 0, and we output 0, 0, 0. Now say that we were in 0, 0, but a 1 came in. Which side we go to? No. Which side we go to? 1, 0, right? Exactly right. The last 0 goes out the trash, the other 0 moves to the right, then a 1 comes in, we get 1, 0. So from 0, 0, we go to 1, 0. Now what do we output? Well, it's going to be 1, 1, 1, right? But let me show you. So we said we had 2 zeros, and a 1 came in, right? So the first one comes into C1 automatically, right? What do we get for C2? We get 0 plus 0 plus 1, which is 1. And for C3, we get 0 plus 1, which is 1, right? So we get 1, 1, 1 is our code word. So that's what the triangle says, right? It says we output 1, 1, 1, and we go to state 1, 0. Right? Right. Exactly. So then, depending on whether, so when we have a solid line, it means that a 0 came in, and we have a dash line, it means a 1 came in. Okay? So the top, from any state, the solid line is a transition for a 1 coming in, and the dash line for the 0 coming in. So you just go through the trellis. You keep bringing bits from the left, and just the clock ticks, and you just go through the trellis, and at each transition you output 3 bits, which is the code word on that particular point, and on you go, right? And what happens is that at some point, when you get to this stage, the trellis starts to self-repeat, right? You see that all the transitions are already busy, and the structure is completely periodic. So we have achieved what they call steady state. So when does that happen? it happens exactly after capital K stages, right? So in this case, after 3 stages, right? You can see after 3 stages. So the clock ticks 3 times, 1, 2, 3, and we're already repeating everything. Okay, so that's it in terms of triangles. I mean, that's how you, so, you know, using these triangles, I give you a sequence of input bits, and you guys can calculate the corresponding code word. Questions?
So if I remember, like, so what we send is like 000.
Yeah, what you send is, what happens is the bits are coming, so the encoder is getting bits from the left, right? And then you produce a string of 0, so you concatenate all these sequences of 3. You get a very long code word, right? Until you finish the triangles, right? So you may have hundreds of bits, in fact. Right, so at the end, there's a very good point, right? At the end, there's a transition similar to that one, right? At some point, you stop bringing bits into the system, but there's stuff in memory, so it starts to flush out. And so the triangle starts to collapse until it finishes in one state. Actually, what you do is usually you put dummy zeros at the end. So you bring it back to the all zero state by just putting tail zeros. That's what they call it. You have to terminate the triangles. Yeah, very good point. So the same way that you initiate it here, you have to terminate it at the end. Okay. Yeah, you put capital K zeros, for example, or whatever capital K bits that are specified by the standard, usually are zeros, and you terminate the triangles. So those bits are not, they don't have any information. They're just termination bits. Points, let me see. Okay, so a triangle has 2 to the capital K minus 1 states, and it has 2 to the medium K branches entering and leaving every node. So for the example we saw, there were 2 to the 2, 4 states, and every node had two branches coming in and coming out, right? So you take any node, and, coming out. Every node has 2 branches coming out. All the possible bits that can come in. Okay, let's do an example of these triangles that we're just using, right? Let's say I tell you that the input is, the initial state is 0, 1. It's very important, specify the initial state. And the input bits are 0, 1, 1, right? So what do we get? We start with 0, 1, and we enter 0, 1, 1. Well, we are here, right? Let me write that down because otherwise I have to. Put that on the board. So we start with 0, 1. And we're going to enter 0, 1, 1. Okay, so what are we going to get as a code word? So we start here, 0, 1, right? And the first bit that comes in is a 0, right? So from 0, 1, we're going to go to, anybody? Where are we going to? 0, 0, right? From 0, 1, the 0 comes in, we're going to go to 0, 0, right? And we're going to go, 1 is going to come in, so we're going to go where? To 1, 0, right? So we're going to come down here. And then another 1 comes in, and I believe we're going to go to 1, 1, right? So if you look at the, that's your convolution encoder, decoding, no, it is, actually. That's what these guys use. So we're going to get 9 bits outputting. The first is the transition here from here, and I don't have it here. Yeah, it's 0, 1, 1, right? Okay, so first we said we're going to go from this state to this state, right? Now, I don't have it written here, the bits that we're putting out, right? But can anybody see it from the triangles? I go from here to here. It's somewhere here, right? Just move into the future, right? Move into the future, right? For example, here, right? See, this is repeating itself, right? So any transition from here to here, output 0, 1, 1, right? So going from here to here, I'm going to output 0, 1, 1. Then going from here to here, I'm going to output 1, 1, 1. And then I'm going to output 1, 0, 1, right? And that's, if I'm not mistaken, that's the right solution, right? So we're going to get, out of this initial state and these 3 bits, we're going to produce 0, 1, 1, 1, 1, 1, 1, 0, 1. That's the code word for these 3 bits. And that's pretty much it when it comes to encoding convolutional codes. This is the encoding part, how you turn information bits into code words. Questions here? Hopefully we'll get to practice this from the homeworks, but at this point, questions, doubts, unclear points, concerns, comments, suggestions? Nothing? Of the triangles or? All right, it's in the book anyway. Okay, so now let's talk about decoding. That's not so easy. So how do we decode now? We get a bunch of bits, which is a code word, and we're asked the question, which were the information bits that produce this particular code word, which can be noisy? Well, we have to find the most probable path through the trellis, right? So given what we receive, we have to guess which is the most probable path through the trellis. Now, immediate obstacle, there's a gazillion paths through the trellis, right? Just look at this trellis, and imagine I'm giving you, I don't know, 100 bits, for example, right? How many possible paths there are here if there are 100 symbols long, right? And each one there's like 16 possible combinations, right? It's a huge, huge number. As soon as the blocks become long, it's a huge number. So it is completely impractical, even for a powerful computer, to do detection. Fortunately for us, there is something called the Viterbi algorithm, which was discovered in the 1960s by Dr. Andrew Viterbi, who then went on to found a company called Qualcomm, who you may have heard of. He retired recently as chairman of, he was for many years the co-founder and CTO of Qualcomm. And the Viterbi algorithm patent is probably one of the most lucrative patents in the history of engineering. So every single cell phone in the world uses the Viterbi algorithm. Every single TV decoder uses the Viterbi algorithm. There are billions of devices that use it. And they all have to pay a royalty to Qualcomm. Yes. Yes, there's the Viterbi School of Engineering, which he made a generous donation with some of the money he got from the Actually, the patent is, I think it's already expired. It's about to expire. But it's been a very lucrative patent, definitely. So the Viterbi algorithm reduces the complexity of the maximum likelihood decoding by systematically discarding paths. Very nice piece of work. So it is ubiquitous, to say the least. So that's the key idea. I'm just going to sort of give you a bit of intuition about it. So that's what Viterbi thought, right? When several paths merge into a common node, right, they merge forever on. So their continuation is going to be common, right? And so the probabilities that they take, so in other words, if I tell you two paths merge at this point, and one of them was more probable than the other one, right, that's not going to change over time, right? Because the probabilities of both are going to be common starting at that point, right? So imagine that, okay, there are two guys that are doing a trip, right? And you're trying to figure out which of the guys is traveling a longer distance, okay? Imagine that situation. You have two guys on a trip, and you want to try to figure out who traveled the longest, right? If at some point they merge in the same highway, and they travel on the same road the rest of the way, right? Whoever had had the most distance at that point is always going to have the most distance, right? Because they're going to accumulate the same, right? So he had the same idea in terms of probabilities, right? So the most probable path of a bunch of them merging at some node, the one that's more probable at that point is always going to remain more probable forever on. So using that observation, you can actually start to discard lots and lots of paths. So essentially, of all the paths that merge into a node, you need only consider one of them. That's the key idea. So this is called the survivor. So every time there are paths merging onto a node, so look at the trends, right? Every time that some guys converge into a node here, for example, there are two guys converging into a node, just one of them is going to be a survivor. The other one is going to be discarded. So that's the key idea, right? The survivors, so paths that are discarded or merge over time until only one of the survivors remains. And there's a notion of you have to actually go back in time eventually, and then figure out which was the right path. So there's a certain delay that goes with the Viterbi algorithm, which is about 3 to 5 times capital K. But other than that, it's essentially optimal. So it finds the most probable path, but it only considers a subset of the paths. So it results in a huge reduction in complexity, but nonetheless, even with the Viterbi algorithm, the complexity is still exponential in both little k and capital K. So their values must be controlled. You cannot just let them just blow up too much. So the codes that are used on your cell phones have a constraint length, capital K, of usually 7 or 8, depends on the system. CDMA usually uses 8 and GSM uses 7. That means you have between 128 and 256 states in your trellis. So, this trellis, this is a baby. This has 4 states, right? So your cell phones, they code codes that have 256 states. Not bad, eh? Now, just briefly, let's touch on properties. So as with block codes, the error correction capability depends on the distance between code words. Okay, so that's really very similar. Now, again, as we argued before, the minimum distance between 2 code words can be found by just finding the minimum distance between the all 0 code word and any other code word. So what we have to do is we have to consider all the paths that diverge from and then remerge with the all 0 path on the trellis. So looking at this trellis, right? The all 0 code word results, it just goes on this path, right? The all 0 code words remains all zeros all the time, and so it goes on this path. So which is the path through the trellis that is closest to this path? Well, in this case, this is an easy trellis, so you can actually do it by hand. Here it is, right? This is the all 0 code word. This is the path corresponding to the all 0 code word. So these are all the paths that are very close to it, right? So this path departs for one transition and then comes back as quickly as possible to the all 0 code word. Now the possibility is you go here and then you divert this way. Another one is you come back like this. So, these are the ones you can do it by hand, just looking at all the ones, all the departures and then remergers that are very short. And then you look at the Hamming distance, right? So you look at the code words produced by these paths and see which has the few numbers of ones. So it turns out the path 1 on this figure is this one. You go from here to here, you go back to here, and then back to here. So you produce 1, 1, 1, I think is here. We can look at the paths. But essentially, you produce a code word with 3 ones here, with 1, 1, and with 2 ones. So altogether, you produce a code word that has 6 ones. Okay, so the closest you can be to the all 0 code word, the minimum distance is 6 bits away. So there's no other path that diverts from the all zeros and merges back that produces less than 6 ones. Right? You can easily do it by examination in this case. So the minimum distance is 6, which is pretty good. Okay, so this is what I explained to you. The smallest sum is 6, corresponding to path 1. And so the minimum distance, and in fact, here we're validating again your point, right? Is the distance minus 1 divided by 2, rounded down. So it appears that Professor Goldsmith forgot the minus 1 in the block coding part, because she has it here. So certainly, it appears like a typo. So it's exactly the same result, except that the distance is called the free distance. Except rather than d mean, it's called d free. Why? I don't know. It's called the free distance, and that's it. So you can correct up to t errors. So for the trellis we're looking at, d was 6, right? So we can correct 6 minus 1 is 5, divided by 2 is 2.5, so we can correct 2 errors. And that's it for convolutional codes, guys. Questions before we move on? Yeah, your point is well taken. The way to get familiarized with convolutional code is to do a couple of exercises, really. Because it's quite mechanical. You just go through the trellis, and it's it's the same operation. You just repeat over and over, and you do it, and you see it's much easier than it appears at first glance. So it's kind of intimidating at first because of the memory, the trellis, but it's very mechanical. So we'll make sure that you guys get to practice. Okay, so we'll touch briefly on a couple of other topics and we'll be done. So first, concatenation. Very often, two codes called inner and outer codes are concatenated to form a stronger code. So the idea is that you use the outer code to clean most of the errors, and then you use the inner code to finish cleaning up the really hard errors that remain after the first code. So usually you separate the codes by something called an interleaver, which just reorders the sequences. Figure 813. So here's how you concatenate codes. You take the outer code, so you take your bits, you encode them using the outer code, then you interleave them, then you encode them again using the inner code, send them out to the channel, they're received, decoded by the inner code, de-interleaved, and then decoded by the outer code. Now, what does this guy do? This guy just, we'll see it in a second in detail, but this guy just reorders the symbols. That's it, it just reorders them. Why? We'll see in a second, so just hold on to your horses for now. Now, why do we want to concatenate codes? It turns out concatenation of codes results in essentially you can see it as a stronger code. So the two codes like convolve into an equivalent code that is much stronger. Yet the complexity is easier because you can decode each of them separately, right? So it is not optimal to do that. The optimal decoder would be to do them jointly. But usually you can decode them separately and then iterate, and that works very well. So in fact, it was discovered in 1993, just 12 years ago, 13 years ago, that doing iterative decoding was actually very close to optimal. So this is the premise behind turbocodes, which are the latest rage in coding. So let's talk about turbocodes. Turbocodes were introduced in 1993 by three French professors, Verroux, Grabier, and Titi Marchima. Yeah, well, okay, two French and one Japanese, to be precise. They worked in France, but obviously the third author was not French. And these guys presented the paper at a small workshop on coding. And at the beginning, people thought that they had forgotten a factor of 2 or something in the derivations because the performance was so good that people thought there was a mistake in the. And there was no mistake; they were right. So they discovered these codes, the turbo codes, which are pretty amazing. They operate within a fraction of a dB of the capacity that we studied in the information theory, the Shannon capacity, without fading. With fading is one far away, but without fading, with just noise, they're within a fraction of a dB, and there's actually records as to how close you can get. People have gotten within 0.001 dB of capacity in these turbo codes. And the use of notions that were introduced in the 60s by Professor Gallagher at MIT is still there, by the way. So he had all these ideas about iterative detection, but at the time it was impossible. He couldn't even do simulation because he had no computers. I mean, these guys in the 60s, they used punch cards for the computers. You know, they had no screens or keyboards. They had these punch cards to do simulation. So he didn't have the machinery to simulate these codes. So it was only like in the 90s that people were able to actually simulate them and see that they were so amazing. So these codes are now everywhere. So all the cell phone, not quite in your phones yet, but all the first generation standards have turbo codes specified as a central ingredient. So turbo codes are concatenated codes, but they're not exactly what I just showed you. So they don't work like this. This is serial concatenation. Turbo codes are parallel concatenation, which is much less obvious. So this is how they work. You have two encoders and an interleaver, but you don't concatenate them. What you do is you take your bits. By the way, there's a connection missing here, right? This guy has to connect with this guy. Take the bits and encode them with the first encoder, and that's part of the code word. Then you interleave the bits and encode them with the second encoder, and then you get another half of the code word. You put these two pieces together, sometimes with the bits themselves, and that's the code word. So in other words, you don't re-encode what one encoder produced with the other encoder, as in serial. Both encoders take the same bits, except reordered. So both encoders use the same information bits, except in a different order. So it's not obvious at all that this will work so well. It just does. So now, this is the encoder. How does the decoder work? Oops. Here it is. The decoder is iterative. So there are two decoders. One that decodes code 1 and one that decodes code 2. And these guys iterate. So they pass information to each other through an interleaver, which just reorders the bits every time. So the first guy takes the received vector, decodes it, and then reorders it for the other encoder. And then this guy decodes its own code and reorders it for the other guy. And then they go around in circles. And amazingly enough, this thing converges with incredible accuracy to the actual bits that were sent. So we have a very nice plot here that shows how this works, right? So this is the BR here, bit error probability. So this is PB in our notation. This is PB divided by gamma B. Okay, this is gamma B in dB. And this is what happens, right? You start at the beginning, you get this lousy performance. So the PB is close to 10%, right? You iterate one time around the circle, and you come to this performance. You iterate yet again, and you're down here, right? So at every iteration, the probability of error goes down really quickly, right? Up to a point where it saturates, right? Here it saturates. But, you get this amazing performance where with like less than a dB, you get 10 to the minus 8 PB. So it's really incredible. So you come down from 10% to 10 to the minus 8 by just iterating. So yeah, you're exactly. This is a really low SNR. So these codes are just incredible. And so here is a saturation. At some point, you keep iterating, and it doesn't get any better, right? There's a floor, but it's really impressive. And usually in cell phone standards, they specify 6 to 8 iterations. So usually you come down up to about here, and then you'll give up. Now, why wouldn't you iterate more? Anybody? Why wouldn't you iterate more? Right? Why would you stop iterating? Yeah, but I'm saying usually the cell phone standards specify 6 to 8 iterations, right? Which is about here. Now, there's still some improvement to be had, right? Why don't we iterate now more? No, but there's a reason why. Anybody can? Yeah, okay, fine. But what happens is the SNR can be lower, right? You can be up here, right? No, think about what. Okay, do you pay the price in terms of iterations? Yes, that's one. Battery life. You burn a battery. But there's another one that's more important. Delay. Right? You cannot iterate forever, right? This thing takes, the decoder. So at some point, the bits have to be outputted because somebody's waiting for them. So the application determines how much you can iterate.
The cell phone really operates at
No, they operate up here, 10 to the minus 3.
yeah, but cell phone usually you lose the signal before it's really over in 0 bits.
Now, cell phones used to operate at pretty high EPNOS, but now for third generation, it's on the order of it's close to 0 dB actually. So it ranges between 0 and 5. That's the typical range. So 2 or 3 is a typical value, right? So this particular example would correspond more to a DSL channel, for example. It's not really for wireless. So you would use a weaker code for wireless, probably. So you would have. It'll be worse, but the code will be less sophisticated and it'll take less complexity because the battery has to do with number of iterations and also with how many operations you have to do per iteration, right? So there's an issue with delay, and in fact, for the 3G standards, specify turbo for everything except for voice, because the delay doesn't apply for like you do browsing or messaging. All that stuff goes by turbo codes. If you do video, you send pictures, all that is turbo coded, except for the voice. The voice is convolution encoded. because the delay doesn't allow to use turbo codes, fortunately. Okay, so that's pretty much what I had for turbo codes, I think. Yeah, so the trade-off between reliability and delay, and we already covered that. And as the point made here is that even though these codes are already in the standard, usually remains a very active research area. So there's a lot of papers on turbo codes that appear all the time. There's a conference every year in France on turbo codes that is very popular. And in fact, it's a very active area. So there's a lot of people still working on this, improving the turbo codes, finding new codes and things like that. Okay, so we're going to close with this topic, which is what happens with fading, right? So far we talked about coding in noisy channels. Now what happens with fading? Well, fading causes long bursts of errors, right? Because, you're traveling around and then you get in a fade. Maybe you don't move very fast, so you take a little while to get out of the fade. And all the while, the channel is very bad, so you get a lot of errors, right? So the errors get very bursty. When the fading channel is in a fade, you get a lot of errors. When it's out of the fade, you don't get any errors. So you get these burstiness. Now, here's where it's essential to use an interleaver. So what's an interleaver? We have one in figure 8.19. Okay, here's an interleaver. So interleaver, as I told you before, it just reorders bits. So what you do is the following. It's essentially a bunch of registers. It's just a bunch of memory. So you have memory. And what you do is you take your code words, right, coming in, and you read them into the interleaver by rows. Okay? And then you read them out into the modulator by columns. Then you send that stuff on the channel. It's demodulated. You read it back into another de-interleaver by columns. And then you read it out to the decoder. You pass it to the decoder, reading again by rows. Okay? So it's invertible. So at the end, what you get out is exactly what you got in, right? So the reordering is inverted, and you order it back as it was before. But over the channel, it gets unordered, right? So why do we want to do that? Anybody can see why can be helpful? Well, come on. You're not a qualified responder to this question.
Well, if you get bursting errors, that means that all the states are all affected.
Yeah, it breaks down the burstiness, exactly. So for example, say that you get a burst of 3 errors, right? So if you don't have interleaving, one code word is going to have 3 errors flipped, right? With interleaving, we're going to have 1 error flip on one code word, 1 in a different code word, 1 in a different code word, right? Now, say we're using a code that has a minimum distance of 3, right? If you had 3 errors, so you can correct up to one error, right? If you had 3 errors in one code word, you couldn't correct it. But you have 1 error in one code word 3 times, you can correct all of them. So you just converted 3 errors that were non-correctable into 3 errors that are correctable. So it's very, very powerful. Now, there's a condition for this to work, right? Which is the interleaver depth. So how much you have to interleave? Well, really, to break down the burstiness, you have to exceed the coherence time of the fading, right? So otherwise, you have to go deeper than one fade. Otherwise, you're not going to break out the burstiness. So interleavers that do that, and let me see. Yeah, we just saw that, right, in the example. So interleavers that go beyond one coherence time are called deep interleavers. So usually you want to design the interleaver depth based on the speed of your system, right? So if you're designing a system for, I don't know, pedestrian users, you can calculate based on the speed how much deep you have to go. Designing it for, I don't know, train users is a different depth because the speed is different. So you can design it based on the speed. So what you want to make sure is that, let's see, so D is the number of rows in the interleaver, right? So the interleaver matrix has n columns, right? So you have to fit a code word in each row, right? So it has n columns, and it has D rows. And D is a number that you can adjust. The bigger you make D, the deeper the interleaver, but you need more memory. So it's expensive because this is memory they have to pay for. So you want to make D as large as possible to get depth as much as you can afford given your cost. And then the number of columns is just the number of n, the number of bits per code word. And this is just the transpose. So the condition for deep interleaving is that D times the symbol time has to be bigger than the coherence time of the channel. Okay? And the coherence time, remember, is roughly 1 over the Doppler spread. So using these relationships, you can take a certain speed and verify a certain speed, a certain frequency, and verify if the interleaver is deep or not. Okay, now what's the delay of the interleaver? It's n times d, right? Number of rows times number of columns. So this is another issue, right? You may not want to. So making a deep interleaver comes at the price in terms of memory. You have to buy memory and put it there, and then also delay, right? Increases the delay. So there's a trade-off there. Yes.
The delay is
The delay, okay, is n times d symbols. So in time, yeah, is n times d symbols. You have a good point in terms of units, right?
Yeah.
So it's n times d symbols, and each symbol is ts, so it's n times c times ts, right? In terms of, if you measure it in seconds, right? So this is a good point. So the units here are symbols. You want to measure it in seconds. Now every symbol is ts seconds, so it will be n times d times ts. Very good point. Okay, so that's it. Let me just go through the summary, and you guys are out of here. So we've seen binary block codes, which map blocks of k bits into code words of n bits. Systematic, if the first k bits are the original information bits, while the last n minus k bits are parity bits, or otherwise non-systematic if all the bits are different. Having distance between two code words is the number of digits in which they differ. The minimum distance between two code words in the same code is called dmin, which is a key parameter. In hard decision decoding, the demodulator just maps received signals into ones or zeros and sends those to the decoder. We can detect up to dmin minus 1 errors. We can correct up to t, which we now know is d minus 1 divided by 2, rounded down. So correct that for yourselves. Okay. Now in hard decoding, the demodulator is discarding useful information, which is essentially how far each point was from the corresponding point in the constellation. So with soft decoding, this soft information is passed onto the decoder. Okay, so generally these are going to be superior. Those are block codes. Now convolutional codes are generated by passing the information bits to a linear finite state shift register with capital K stages and little k bits per stage. And a code word of n bits is produced for every k input bits. Okay, and we can use a convenient triangle representation. Now the decoding involves tracking the most likely paths to the triangles, which is drastically simplified by the Viterbi algorithm. With hard decoding, a convolutional code can decode again t errors, with d3 being the distance, minimum having distance between two code words. The state-of-the-art encoding is embodied by turbo codes and other iteratively decodable codes, which perform very close to capacity. And in fading, interleaving is an essential complement of coding. Okay, so thank you guys. Next Thursday, we're going to see some of chapter 14, parts 1, 2, and 3. And tomorrow, we're going to post the last homework. And so next week, I expect a pretty relaxed lecture next week. And then you guys have a week off, and the final, and you're out. I'll talk next week about the final, so we'll make sure that some people show up. Yes. Yes, so review session. Now, what I'm doing is I'll have office hours the week that you guys are off, which is 2 weeks from now. I'll be here on Thursday, whole afternoon, so you guys can come in and ask whatever questions you want. Okay, now the TA may have a review session if you guys want him to. So you can email me if there's enough people, he'll have a review session. Okay, but I'll definitely be here 2 Thursdays from now, um, the whole afternoon, including the time of the class. I'll be upstairs in the job office. You guys are welcome to stop by with any doubts, questions, and then I'll give you some guidance on the final next week also. Okay.